I looked up data from a Ford 350 pickup truck. It's actually kind of hard to find the mass of the rotors. I found it to be 24 to 36 pounds. So we're going to use that. Now, if we are going to pick an example and we wanted to maximize our heating, so we want to know the extent, how bad could the heating get, should we choose the lightest example or the heaviest example? The maximum weight that a Ford 350 pickup truck is 9,200 pounds. It can have up to 1,900 pounds of cargo as well. So my figures seem to be 11,100 pounds. And of course, highway speed is 100 kilometers an hour. But let's take an extreme example. This guy, he's an owner of a truck, so he probably drives at 140. The rotors have a weight of 33 pounds each, and there are 4 of them. They are typically made out of cast iron, which has a heat capacity of 0.49 kilojoules per kilogram per degree. This means that if the brake rotor warms up 1 degree, that 1 kilogram of that brake would have needed an extra 0.49 kilojoules to heat it up, 49 joules, significantly less than what you need to heat up water. So we want to know is how hot are the brakes going to get when this guy slams to a halt? Can we calculate that? Certainly. First thing we want to do is convert the 11,000 pounds to kilograms, which is a very simple conversion you can look up anytime you need to. That's 5,000 kilograms. Highway speed has to be turned to meters per second, and the conversion for that was to divide by 3.6. So 140 kilometers an hour becomes 39 meters a second. How much energy does the truck have while it is at that speed? We use kinetic energy. And the kinetic energy of the truck, okay, I goofed with my numbers here, rounded differently, doesn't matter. If you did that to me on a test, you showed me your steps, but you accidentally swatched a number out, I would still give you the marks if I can clearly see your train of thought is demonstrated. So multiplying these out, I get 3,600,000 joules. I'm going to ballpark it. That's 40 times 40, that's 1,600. 1,600 divided by 2 is 800. 800 times 5 is 4,000. 4 million. I'm ballparking 4 million in my head. So that number's correct. The brakes are going to have to eat this. When that vehicle comes to a halt, assuming it doesn't skid, lock the tires and drag them on the road, they stop properly so the wheels continue to spin, then those brakes are going to have to swallow all 3.6 million joules. There are 4 tires on the truck. We have approximately 4 million joules. So each tire is going to have to eat 1 million joules of energy. All of that million joules will go into heating the brake rotor. So knowing the heat, the energy that's going to be turned into heat, the mass of the rotor, and what the rotor is made out of, we can solve for temperature, and we get this formula. And all the heat energy is coming from the kinetic. So we'll plug in our numbers. Delta T is going to be Q over M and the heat capacity. We've got to be careful. We've got prefixes. So 4 million joules is that. 0.49 times 1,000 is boink, boink, boink. We get 490 joules. We type this in on our calculators, and we get a temperature change of 1.6 degrees. Are we right? Well, let's see. 4 and 6 zeros. Take away 1, 2, 3. That's 4 with 3 zeros. 4 over 5 is essentially 1. And 1 divided by this This is about 1.5. Get 1.5 degrees. That doesn't seem like much. Sure, I did that right? Seems right. But I know when I stop a vehicle and I've touched a brake rotor, tell me I've done it. Yeah, it hurts. This seems wrong. So what's our mistake? Hmm. See my mistake? We have two separate masses in this problem. The kinetic energy was based on the mass of the truck. The heat energy is the mass of the rotor. I stuck the mass of the truck in here again. That's the mistake. Little slip-ups like this occur all the time. Why do you think we like using subscripts? You needed the rotor mass in here. Now when you carry it out, you get this walloping amount of heat. Now 600C, wow, that seems really big. That's gotta be wrong, isn't it? See my second mistake? Think about it. Let's go back up. Right here. There's my mistake. All 4 tires are getting this. Should be 1/4 of that, and I put in the mass of the vehicle, not the mass of the rotor. So at this point, everything you do is wrong. And I can't really give you part marks because you didn't label anything. So then you fix it. You fix the first mistake, and this is like getting your melting point. That's ridiculous. A fire would break out. And then you go, wait a minute. You got to think about what you're looking at. And once you fix that, you've got a reasonable number. It'll burn, but it shouldn't be getting to the point that's well beyond the flame temperature of paper. You'd have fire breaking out. The tires would burst if you got that kind of heat. Okay, so 2 simple mistakes. How do you avoid that? Label what you're doing. Identify, think about what it is. Mass of the rotor. Use a subscript. Change your colors. And tell me your steps. And if you tell me your steps and you make silly mistake with numbers, I can still salvage your mark because I understood what you were trying to do. So now you are able to do this. One of the nice things about the newer rotors, the iron ones were only about 0.5 joules per gram per degree C. These ones are as high as 0.72 to up to 2. Well, that means this rotor would take 4 times the energy to heat to the same temperature. So many of the newer rotors don't actually get as hot either. And so this really extends their life. And we can talk about rotor science more if we wanted to, but from a calculation viewpoint, that shows you how to do a basic calculation and look for 2 of the most common errors. The trick in science is these things have meanings, and you should be able to hunt down your mistake on logic.